So today I'll be talking about, the predictive maintenance and how digital twins are enabling that predictive maintenance in a number of different applications that we employ at General Electric. First, some acknowledgements, and I put some references here. So most of the technical material that is included in the presentation can be referenced through these technical papers. Just to give a very brief overview, because most of us, we know fairly well what GE is, but not much is talked about GE Research. And so it's a private research organization, and we have recently adopted a new model where we are going external and talking to government and even external partners. So you can see it's a fairly large size organization, 1,000 plus researchers, about 600 PhDs and all. But on the top right, you see the kind of assets that we are really dealing with. So we are looking at gas turbines. A large majority, a large portion of energy or the electricity that is generated is through GE gas turbines. We have CT scanners all over the world. Of course, a large chunk of engines in the aircraft that flies are GE engines. Wind turbines, and wind turbines are growing globally. Oil and gas and additive, and you name it. So there is a large number of applications, and GE has been at the forefront of predictive maintenance since last almost 2 decades now. So a lot of work has been done, and AI and machine learning has been part of the core research or core analytics that GE has been employing. Now, with the advances in recent AI and machine learning methods, what has really changed is things that were not earlier possible are becoming possible, right? So the modalities of how we collect data, how we measure the health of the system or visualize the health of the system is becoming very, very different than what it used to. So we have a lot of, so in our group, we have a lot of image analytics, natural language processing, and of course, time series analysis. And now what's really happening, now that all this information is becoming available to us simultaneously and we can process it, we are taking advantage of learning from this multimodality of data, right? So not only I'm going to be looking at the sensors that are coming, telling me something about the health of the system in a locomotive, I'm also looking at the camera and it's telling me about the health of the track, right, in real time. Likewise for jet engines, wind turbines, gas turbines, you name it. So I won't dwell too much on this, but I just wanted to use this slide, and I assume that most of us would be very familiar with the chart on the bottom of how predictive maintenance has evolved over the years. And what we see that up until PHM, when we talk about models or systems, they tend to be more fleet oriented, right? So when we learn or when we learn from systems, they kind of give us fleet level models. And with digital twin, there are a few things that are changing. So of course, we are adapting those fleet level models to individual assets. But at the same time, there is a need that we keep evolving those models. So continuous learning becomes very, very important. And that's where we are seeing that being able to use these digital twins allows us to do predictive maintenance in ways that were not even possible, a few years back. Again, this just says different industries I have personally been involved with in my last 5 years at GE Research, and that's really the variety that I enjoy here, to get to see the nuances of how things are different in different industries. Essentially, at the top level, it's the same problem. Being able to detect anomalies early, being able to diagnose what it is, and be able to predict what can be done, or what should be done, and how it should be done. But given different industries, the way data are collected, the way maintenance processes are implemented are quite different. And from an algorithm's point of view, all these become quite important to keep in mind. So we most of the systems that we work with, they are high value assets, as in a jet engine could cost upwards of $200 million, right? And then of course its maintenance and operating cost is totally separate. Likewise, gas turbines, or if you talk about locomotives, they're all very high value assets and critical assets. So we cannot let them fail while they are operating. And it becomes very important to make sure that when these systems go out in the field and doing whatever they are supposed to do, there shouldn't be a catastrophic failure. For that, these systems have been instrumented fairly well, and we have been monitoring these systems. So one of the G business model is about services. So we sell the asset, but at the same time, we are actually selling the uptime or the time on wing, let's say, for jet engine. And what that means is we have to continuously monitor those engines. And when the analytics produce any alerts, we have analysts who are sitting in our remote monitoring and diagnostic centers. They might request more information from those assets and be able to come up with some hypothesis so as to what might be wrong. They might call the operator and ask for some more information, or they might be able to pull more information from the data lake and be able to say what needs to be done about those assets. Now, with AI, we are trying to move towards where all of this manual glue that we are providing through this remote monitoring service engineer to kind of automate that piece, right? So we can still assure that these assets will be performing, but can we automate, can we add more smarts to it? Because now we have information available from different sources of data, and can we all put together all the evidence coming from different sources and be able to make use of that? So one example I picked from power industry, and this is somewhat my assessment. So if you look at on the left-hand side, when we talk about PHM, these are different segments that I'm dividing PHM into. And on the right-hand side, I put some examples, what these could include. Now, this is not an exhaustive list. I just put some. And if you look at the power industry, this is where the maturity kind of lies. And on the x-axis, what we see is, the growing network of how these assets are connected. So, for instance, here we are talking about core assets in generation. So it could be the main gas turbine or the hot section of the gas turbine. But then we have balance of plant, which is all other equipment outside. Then we are talking about the fleet. Then we're talking about transmission, distribution, and all the way to the residential or the commercial complex where the electricity is being used. And we could be monitoring, because if any of these in the chain breaks, the customer loses power, right? So all of this PHM has potential value to keep all of these running and keep them operating at the maximum efficiency. So this is kind of my view on where the relative maturity is in terms of these different pieces and which parts of the industry where we are seeing more effort being applied to build these. Okay. So let's talk briefly about the digital twin, and because I would like to define it, and I have talked to a number of people, even within the company, and of course outside the company, and there are a number of different definitions or understanding of what people think digital twin is. So from our perspective, we think that any engineering model that can continuously add insights into each asset to deliver a specific business outcome, right? So there are three key bullets or key points here. So they are engineering models, and they are continuously adding insights, they're continuously monitoring the asset, and they are providing some information about the asset as it is operating, and it has to drive some business outcome. So when I say per asset model, it means that, yes, I may have trained my machine learning method based on data coming from 7,000 jet engines. But when I am monitoring this particular jet engine, I want my model to best adapt it to this particular jet engine, because each jet engine, it flies in different environments, and it flies with different, through different operators and very, very different operational mode at times, depending on what part of the world it is flying in. So my model has to be adapted. So it has to be per asset, because I don't really care on an average how my fleet is doing, because I need to make sure that this particular jet engine, when I take this flight, is operating properly. It has to drive some business outcome, and I'll show some examples of what those might look like in our case. They have to be continuously tuned. So as assets degrade or they develop faults, they have to be continuously tuned. They have to be scalable, so we can deploy these models to all of our jet engines, and they should be adaptable. So as we were just listening to the previous speaker, where we have a good model that's working for this model of the jet engine, and now GE comes out with a new jet engine, can we adapt that jet engine instead of developing also a new model? So these 5 attributes define our digital twins. And when we look at the business outcomes from our perspective, we have to be able to do any and all of these things, right? So where and this is where AI really comes to rescue, because a lot of these things can be done with AI and traditional signal processing based methodologies together very effectively. And again, to define digital twins, they can be different kinds of models. So we can have an asset twin of how a jet engine performs. It could be a process twin, how it is maintained, or how it is deployed in service. Then it could be the industrial plant twin. So as we were talking in terms of the gas turbine, so how the gas turbine operates, but at the same time how the entire plant operates around it, or how the fleets operate around it, and of course how the business is done. How do we measure the success of the success of these analytics? And all of these twins, they can be connected, not necessarily through the same, let's say, same programming language or that kind of platform, but they should be interconnected. So if I need to gather data from or get more evidence at different levels, I should be able to make connections or contextual connection to any of these. And we have been looking at data technologies like knowledge graphs and things like that, where we connect the outcomes or these different types of models together to make it all work. So the core idea that came from, for our digital twin transformation or digital transformation was from this. If you look at all these companies like Apple, Amazon, and Google of today, they moved from building a digital model of a person, as we call it, as a demographic model. So we know this person resides in this area, and that's how the recommendations used to be, to build it more psychographic model, where we say not only they are of this gender or this age range with this income group, we are able to do more because now we have more information around it, right? Then the business outcomes used to be few, but now and they used to be targeted towards the group. So for this kind of people, we should be driving this type of business outcome. That has moved to profiling an individual and giving you individualized recommendations. So again, you would see that we are moving towards individualization, and that's where the per asset model idea comes from for our digital twins. And of course, as we drill down and go to single asset level, we have to make sure that we have a platform that works for all of these in a coherent way, because now we cannot afford to build models for as many assets if they did not scale. So in the context of our engines, or our applications, you can see that earlier the models used to be some sort of reliability based or on an average. Let's say we would talk about mean time to failure type metrics, but now that is moving towards what can I say about this particular engine, because I know a lot more, where this engine flies and how it is maintained and things like that, right? So from Per asset model, we have analytics that are also per asset. That's the model that is tuned to that asset, and then we should be able to customize the recommendations or whatever those business outcomes are to those particular assets or industry segments. So one example where the digital twin for the gas turbine, it could include lifing models. So these are reliability-based models and damage accumulation-based models. Then we have health models working together for certain components, thermal models, transient models. These are different models. So you can see all different kinds of data that go in, and then we also have to take into account what the customer KPIs are, and then these different business outcomes can be driven by that. So let's jump into where AI is working and what are we doing in terms of using AI to accomplish all this. So I just put some high-level bullets, as in, so we are starting to look at a lot of image and video analytics, where real-time video analytics allow us to do some inspections and collect data about the health of the assets. One example that we are recently working on is drone-based inspections of offshore wind turbines, where the turbines are actually in operation or they are moving. We move them slightly slow. We don't stop them, but at the same time, the drone can be managed to get the images that we are looking at. A lot of work is being done in natural language processing, because the logs that get generated by all the processes, especially in the maintenance area, they have a plethora of information. Not all of that is captured in our sensor data, or something that we cannot explain based on what we are seeing in our sensor data. We can make that connection through by analyzing those maintenance logs. Time series, of course, has been our bread and butter in terms of PHM applications. Then a lot of work is being done in robotics, where can we do things automatically? Like for instance, a lot of rounding or repair actions, can they be done, especially in hostile environments? So we are doing a lot of work in there. Then comes the science of AI, where we are looking at some fundamental questions, because when we want to automate this, there is a big gap between technology and the automation, at least in the industrial area, because we have to ensure some sort of robustness. We have to be able to explain why AI said something, what it said, and be able to add some sort of common sense reasoning to AI outputs, so it all makes sense to humans, because we don't see this becoming completely autonomous, at least in the industrial area for many applications, anytime soon. And of course, decision automation is another piece where we are using a lot of AI technology. So where are the challenges? And this is where I will focus here. So being able to explain what we are doing, through our complex models is very, very important. And at the same time, establishing trust into what AI is saying is very important. So I'll focus on these two pieces through some examples that we have been working in the last few years. So let's look at explainability, and we have built this model, what we call as deep analysis net with causal embedding. Here we are. So usually when we look at deep, typical deep learning models, they are unconstrained low to high level connections, right? And that makes it very hard to interpret why the model said something what it said, right? Especially in the time series domain. In images, we know this can be done now, but in time domain, it becomes very difficult. So we have built this model, and you can have more details, in some of the publications, where we have designed these layers to model the nuances of the factors in time series that we are interested in, the way we can accentuate the effects of faults, and how can we visualize them at different time scales, right? And these models, they can not only help us detect the faults in time series in time, but at the same time give back information about the causal factors. Why does the model think based on this data that we have some fault? So we take the original time series data, and in our situation, we have, let's say, traditionally we have been building analytics where we know about faults, and we can build analytics, either physics-based or data-driven analytics, to detect certain bearing and gear fault, let's say. But what we are interested in here is, can we monitor the entire system in an unknown sense? So there are these issues that we have never seen, but can we still find or detect some anomalies? So it's essentially an unsupervised problem that we are after. In that case, we take this window-based approach where we create a sample, and we want to predict next few instances in that sample in our multivariate time series. And we then train our model based on data. So for instance, in one application on jet engines, we are using data from over 200 million flights, and then across different operators on a single type of engine, and then using that model to scan the fleet on a monthly basis or a bi-monthly basis to see what are the assets that are trending anomalous at any given point, and given the causal factors that this algorithm provides us, we can give some clues to the technicians so they can look further into what's really going on. So it provides us two key things. One is it provides the system-wide coverage. So for instance, the chart on the right-hand side we are seeing, it is modeled based on 300 plus parameters coming out of the jet engine, right? And on the time axis, we are seeing residuals being generated by this algorithm over a period of 6 months. And we can see that in certain parameters, we start seeing trends very early, right? And what we can do with that is, so we model the system together, all parameters going in. But what we can do is we can either create a global anomaly score where we can somehow aggregate all these residuals to get a trend like this and declare an early warning based on how the trends are looking. Or at the same time, we can, looking at what subsystems we are seeing these trends in, we can say more about where the technician needs to go and look into it. So this is one outcome that we are deriving out of this. Second, as a byproduct of it, it tries to learn some nonlinear correlation between different parameters, right? So if you look at one of the layers within the model, we are able to get this type of adjacency matrix where the parameters that are related to each other, we can get some sort of nonlinear correlation. Depending on what is the resolution of data and what resolution of window or in our data preparation we are working with, we are able to derive, we can call them in some cases the causal reactions or causal influencing factors between different parameters. So what parameters changes causes the change in other parameters, right? And in one of the papers, we have provided a few examples as listed here, where we have identified. So if you look at a particular cell, we can say that this particular parameter is affected by all these parameters with this type of weighting function, right? And we then go back to our domain experts and ask them, hey, does this correlation or this causality make sense? And that's how we go into validation in making sure that our model is learning something very meaningful, physically meaningful within that domain, and not really learning an artifact of data. Now, what we also do is, so if you look at the data learned or model learned from fleet, the causal graph could look something like this, which makes perfect sense. But when we look at the unhealthy asset and we further learn or adapt this model with data or recent data from this unhealthy asset, we see that this causality kind of goes haywire. And the difference between the two gives us clues so as to what are the causal factors that are resulting into this change in causality. And that gives us a good clue into what we should be attending into. Last topic is on information to action and trust, and which is really, if we train a machine learning model and we show it as input sample, it will give us an idea or a prediction that what it thinks it is, right? But what is more important, that if somehow AI thinks, or we can make it think that yes, it will make a prediction, but at the same time, it can tell us that it is not very confident based on some belief or some evidence, then accordingly the operators can take action whether to trust that or not. And that's another area that my group has been working on for the last couple of years. So if the model says that this is a fault that I know about, and it cannot go towards automation and say, go take this action automatically. But on the same time, it should also be able to say that I'm not sure if this is the fault, or I have been able to distinguish between 1 and 3, and it needs more evidence. So it should be able to summon that more evidence. Now, that more evidence could come from human or collecting more data, but that is something we need to enable AI or machine learning methods to extract. And this applies to pretty much all systems. So far what's done is we do validation based on some validation data set. And when we show validation accuracy, we say that, okay, this particular individual prediction that my model is making is likely going to be good because my validation accuracy was good, right? But there is no guarantee, because in this case, my system may have been operating in totally different environment, and which if I don't pay attention to, I may get a different or incorrect outcome. So can we do better? And can we look into the observability or the separability of the data? And at the same time, we can also detect when the model is moving into extrapolation zone rather than the areas of competency where it really understands, or it has learned from data. So we have been looking at.
Abhinav, this is David. Can you speak? Can you go a little faster? It's been great, but we're running out of time.
Just 2 more minutes, David. Thank you.
Okay.
Yeah. So in this case, so we are looking at something called epistemology, where we look at, or we try to gather justification, from different pieces of the model. So in a deep learning or a neural network model, if you can look at the geometric support of, let's say, the weights as a sample is generated going through those layers, we can collect that evidence and use that, compose that somehow to come up with justification for whether this falls within I know region versus I may know, or I may not know, or I do not know. So again, there are details available in the references that you can look at. This is one example on wind turbines, and I'll just go directly to this, my last slide, where we have built the system where we are trying to optimize the production of the wind turbines. And in this case, the machine learning models are telling us how to change the derating of the turbine. But based on this humble AI, we are also able to say in what cases we are very sure we have seen these conditions, and we can, whatever the model is suggesting is the control that needs to be applied. And in cases that we haven't seen, we don't recommend action. Instead, we recommend data in those unseen as conditions. So my last concluding slide, in our applications, AI and machine learning has already advanced PHM methods quite a bit through inclusion of different modalities of data as well as new algorithms. But we still see a number of challenges that need continuous research, specifically in explainability, causal reasoning, and trust and uncertainty. So with that, I'll stop. And sorry for the extra time I took, but I'll be happy to take any questions in the next session.